Okay, let's unpack this. Welcome back to the Deep Dive. Today we're continuing our series on the OEIS, the Online Encyclopedia of Integer Sequences. This is really for you, our number theory students, and we're plunging into a specific one, A000300, our mission, to really get what's behind rooted tree enumeration to the fourth power. It sounds complex, but let's break it down.
It does sound a bit technical, doesn't it? But what's fascinating here, A000300, well, it precisely represents the fourth power of the rooted tree enumerator.
The enumerator,
Yeah.
so that's the counter.
Exactly. Think of a rooted tree. It's like a hierarchy, one starting point, the root branches spreading out, like a little family tree.
Okay,
The enumerator just counts how many unique trees you can make with a certain number of nodes or points.
right.
So A000300, it counts something specific.
Right.
Linear forests composed of 4 rooted trees.
Linear forests. So like 4 of those family trees just standing next to each other.
That's a great way to put it. 4 separate, distinct rooted trees, sort of arranged in a line. It's a very specific but quite important combinatorial object.
Okay, that helps visualize it. So to give you a feel for the numbers involved, the sequence itself kicks off with 1, then 4, 14, 44. It ramps up pretty fast.
It really does.
And you can find these long lists. I saw one from Alice P. Hines going up to N500. It's quite something. Makes you appreciate the effort involved in tracking these patterns.
Absolutely. That dedication is key. But how do we actually generate a sequence like this? Where does it come from mathematically?
Yeah, good question.
Well, the real beauty is in its generating function. The definition is GF equals BX raised to the power of 4.
BX. Hang on, isn't that the generating function for A000081? The one for just single-rooted trees?
Exactly.
Yeah.
So BX is like the blueprint for building one rooted tree.
Right.
Raising it to the power of 4, BX to the 4, it's mathematically like saying you have 4 independent blueprints working together. It perfectly captures that idea of forming a forest of 4 separate trees.
Ah, I see. So it's an elegant way to handle what sounds like a really complicated counting job otherwise?
Precisely. It's a compact mathematical expression. And, for those who like to compute, the OEIS entry actually gives you Maple and Mathematica code to generate the terms, shows the link between the theory and computation.
Okay, so stepping back a bit, what's the bigger picture here for us, the learners? Particularly in number theory, why is getting this specific sequence, A00000300, so important?
Well, it's significant beyond just combinatorics, really. A 00000300 isn't just counting, it's providing a kind of model for how certain complex structures can grow.
How so?
For number theory students, seeing these combinatorial foundations can actually shed light on patterns in areas that seem totally unrelated at first glance.
Like what?
Think about problems maybe in theoretical computer science or network analysis, maybe even statistical physics, where you need to count distinct arrangements, different configurations to understand how a whole system behaves.
Okay.
A00300 gives a concrete way to count these specific complex tree arrangements precisely. And we should also mention N.J. Sloan here, the founder of the OEIS.
Right, he actually authored this entry.
He did. And the fact that it's referenced in fundamental books like Riordan's Introduction to Combinatorial Analysis, well, that tells you it's not just some obscure sequence. It's considered a cornerstone, a real building block for more advanced math.
That's a great point. These aren't just numbers, they're foundational ideas. So to sort of wrap it up, a 000300 is the fourth power of rooted tree enumeration. It's key in combinatorial counting, gives us a frame for understanding complex objects, and connects to major figures like Sloan.
Exactly. And perhaps this leaves you, the listener, with a question to ponder. How do these very specific ways of counting things, like rooted trees or these forests of 4 trees, give us deeper insights into abstract mathematical structures? And maybe what other complex systems out there could we potentially model or understand better if we looked them through the lens of similar integer sequences?
That's a fantastic question to end on. The OEIS really is this incredible web of connections, a tool for discovery across so much of mathematics and even beyond. It's definitely a universe worth exploring. Keep diving in.